Some locomotives looked like they were designed by engineers who had lost a bet. Others defied every convention of railway design and somehow worked anyway. From cabs perched on top of boilers to engines that ran backwards, these are 15 of the weirdest locomotives ever made. Let's count them down. Number 15, the Camelback locomotive. This thing looks wrong from the moment you see it. The engineer's cab is perched right on top of the boiler, straddling it like some kind of mechanical saddle. This was not a design choice made for aesthetics. It was all about burning anthracite coal, a cheap but hard-to-ignite coal waste found in the northeastern United States. The solution was the massive Wooten firebox, so wide it could not fit between the wheels in the usual spot. So engineers mounted the cab astride the boiler, halfway down the frame. The firemen got left behind on a tiny exposed platform at the back. Communication between engineer and fireman was reduced to shouting over roaring boilers and clanking machinery, or banging on metal with whatever came to hand. The engineer sat just inches above a firebox hot enough to melt steel, with poor visibility and constant heat exposure. Injury records from the era show Camelback crews suffered twice the accident rate of standard engines. By 1927, the Interstate Commerce Commission had seen enough and banned new Camelbacks, citing unacceptable risk to crews. These locomotives proved that chasing fuel savings could twist a locomotive's shape into something truly bizarre and put the real cost squarely on the people who ran them. Number 14. Southern Pacific's AC-12 cab forward. In a world where steam engines always put the cab at the back, these monsters ran with the engineer and fireman leading the charge, staring down the tracks from the very front. The reason lay deep in the Sierra Nevada, where tunnels and snow sheds trapped smoke so thick that crews sometimes staggered out gasping for air. Smoke choked men and made some runs genuinely dangerous. The solution was radical. Move the cab ahead of the boiler, put the exhaust at the rear, and let the crew breathe clean mountain air even as the engine roared through miles of darkness. This was only possible because the AC-12 burned oil, not coal. Fuel could be piped from the tender at the back to the firebox up front. No shoveling required. Wartime records show these cab forwards hauled up to 7,000 tons over Donner Pass, day after day, with reliability that kept supplies flowing to the Pacific. The locomotives worked hard, running through some of the most punishing terrain in America without complaint. Old-timers called them backwards engines, and some refused to trust a locomotive that pulled with its tail. But for the men who ran them, the AC-12 meant survival. Proof that sometimes the right way forward means flipping everything around and trusting that radical solutions work when nothing else will. Number 13. South Africa's Class 25 Condensing 484. Crossing the vast, dry heart of South Africa, steam locomotives faced a problem as old as the desert itself: water. The answer arrived in the form of a machine that turned its own exhaust into a lifeline. Instead of wasting steam in thick clouds, these locomotives captured it, funneled it through a maze of radiator tubes, and cooled it back into water, ready to be used again. The result was a tender so massive and packed with machinery that it dwarfed the locomotive pulling it. With 6 steam-driven fans and more than 2 miles of radiator piping, the tender looked less like a train car and more like a rolling factory. On a good day, the system could recover up to 90% of the water, stretching the range to nearly 800 kilometers between stops. But all that complexity came at a price. Radiator tubes clogged with scale. Fans demanded constant attention. The sheer weight of the tender wore down the rails. Maintenance logs from the 1960s tell the story of crews battling fouled pipes and failing pumps, sometimes spending more time cleaning than running. The Class 25 condenser was brilliant in theory and spectacular in person, a genuine marvel of engineering that tried to solve an impossible problem. But its thirst for upkeep eventually outpaced even its ability to save water. Number 12. The Beyer-Garratt. This locomotive looks like it couldn't make up its mind. Two engines sit at either end, with the boiler and cab suspended in the middle, floating above the rails. At first glance, it seems bizarre, but this three-part design wasn't just for show. On the narrow, lightly built tracks of Africa and Australia, traditional steam engines sank bridges and buckled rails. The Garratt solved that by spreading its weight across two powered bogies, each carrying its own water and fuel. Instead of dragging a tender behind, the locomotive's supplies rode along for the journey directly under the driving wheels. This meant more weight on the rails where it counted, improving traction without crushing the track. As water and coal were used up, the load lightened on each bogie, but the central boiler always stayed balanced between them. In East Africa, the massive 59-class Garratts hauled trains over 2,000 tons across bridges that once struggled with half that weight. Crews described them as the engine that bends twice, able to snake through tight curves and keep going where rigid locomotives would stall. The Garratt's odd shape and shifting weight made it a handful on rough track, and flexible steam joints needed constant attention. But for the world's toughest railways, it turned the locomotive itself into the train. Number 11. The LNER W1, nicknamed Hush, Hush. This locomotive rolled out of the shops in 1929 looking more like a submarine than a steam engine. Under its smooth, streamlined shell hid the boldest experiment in British railway history, a water tube boiler borrowed from warships. Instead of a simple fire tube design, this engine used a maze of narrow pipes to withstand pressures up to 450 pounds per square inch, promising unmatched efficiency and power. On paper, it was the future. Higher pressures meant more steam from less coal and the potential to leap ahead of every rival on the rails. But the W1's secrets ran deep. Test runs were shrouded in mystery, with engineers sworn to silence and the press kept at bay. Diaries from the National Railway Museum tell of endless hours spent coaxing the boiler to behave, fighting scaling and foaming that clogged the delicate tubes and threatened sudden failure. Maintenance crews dreaded every inspection. One missed deposit could trigger a cascade of leaks. In service, the W1 never lived up to its ghostly promise. It ran hot, demanded constant attention, and spent more time in the shops than on the main line. Only one was ever built. In the end, the W1 called Hush Hush was a beautiful phantom, haunted by the gap between radical ambition and the stubborn reality of steam. Number 10, the Bulleid Leader. Post-war Britain was desperate to modernize, and steam had to fight for its place on the rails. Enter the Leader, a locomotive that looked like a diesel and tried to act like one too. Oliver Bulleid's vision was radical. It was a fully enclosed, double-ended machine, oil-fired, and equipped with a mechanical stoker. The wheels and drive gear were boxed inside a metal shell, hidden from view and shielded from the weather. In theory, this meant cleaner lines, less crew exposure, and easier operation. Just drive from either end, no need to turn the engine. But the reality inside the Leader was far from comfortable. Heat built up in the sealed body, filling the cab with stifling air and engine fumes. The crew sweated through shifts with poor visibility and almost no fresh air. Maintenance teams found themselves crawling through tight, greasy corridors to reach the wheel sets, cursing the enclosure that was supposed to keep things modern. SNCF union minutes from 1950 are filled with complaints about the working conditions. The Leader ran a handful of test trains, but by 1951 the experiment was over. Every unit was scrapped, the bold dream buried under maintenance logs and union grievances. The Leader proved that you could disguise a steam locomotive in diesel clothing, but you couldn't make it live like one. Number 9. The Erie Triplex. This locomotive was not just big, it was a mechanical dare that pushed the limits of steam power into the realm of the absurd. Built by Alco between 1914 and 1916 for the Erie Railroad, this wheel arrangement, 28882, had 3 sets of driving wheels, including one set tucked under the tender. That meant 24 powered wheels clawing at the rails, all fed by a single boiler. On paper, it could generate a tractive effort of 160,000 pounds, enough to snap couplers and rip yard tracks apart. Crews quickly found out that was the easy part. The real challenge began when the Triplex tried to move at anything faster than a crawl. The boiler simply could not keep up, starving the third engine set of steam and causing pressure to collapse above 15 miles per hour. Test data from Erie Railroad records show performance dropping off a cliff once the train left the yard, with the massive cylinders gasping for steam before the train even hit mainline speeds. Maintenance logs tell of endless valve gear adjustments and boiler tube leaks, with downtime far outpacing actual running hours. Yard workers nicknamed it Yard's Ripper because while it could drag a mountain of coal cars out of the terminal, it could barely make it to the next town. The triplex stands as a cautionary tale. Sometimes adding more power just means finding new ways to run out of steam. Number 8. The Pennsylvania Railroad S2 steam turbine. This locomotive looked like something out of science fiction, a 123-foot-long machine sheathed in streamlined steel, driven not by pistons, but by a direct-drive steam turbine. Built by Baldwin in 1944, the S2 was a bold attempt to bring jet-age technology to the rails, promising 6,900 horsepower and a ride smoother than any conventional steam engine. But the heart of the S2 was its gamble. Turbines thrive on steady, high-speed running. On the open main line above 40 miles per hour, dynamometer logs from Altoona show the S2 closing in on diesel-like efficiency, its turbines spinning at full song, burning less fuel per ton-mile than many of its piston-powered rivals. The difference was night and day when conditions were right. But the reality of freight railroading is far from constant. Trains crawl out of yards, stop for signals, and grind up grades at speeds that made the turbine work against itself. At these low speeds, the S2's turbine became a liability. Test data from Pennsylvania Railroad's own records reveal a harsh truth. At 20 miles per hour, the S2 devoured coal and water 2 to 3 times faster than a standard 284. The S2 stands as a testament to radical propulsion, an engine that sounded like the future but couldn't quite live in the present. Number 7. The Kitson-Still steam diesel hybrid. In 1927, British engineers decided that choosing between steam and diesel was for quitters. Why not use both in the same cylinder? The Kitson-Still was one of the most bizarre compromises in railway history. Each cylinder functioned as both a steam engine and a diesel engine simultaneously. The top half burned diesel fuel and the bottom half used steam. The piston was pushed down by diesel combustion, then pushed back up by steam pressure. In theory, this gave you diesel efficiency at high speeds and steam power for starting. In practice, it gave you twice the maintenance headaches and half the reliability. The engine needed separate fuel systems for diesel and coal, separate cooling systems, and a control setup so complex that even experienced engineers needed training to operate it. When the diesel side failed, you could run on steam alone, but at reduced power. When the steam side failed, the diesel struggled to start heavy loads. When both sides acted up, which happened often, you had an expensive piece of modern art on rails. Only a handful were built between 1927 and 1930. The LNER tested one and politely declined to order more. The technology was brilliant on paper, proving that sometimes trying to do everything means doing nothing particularly well. Number 6. The Holman fireless locomotive. Picture a steam locomotive with no fire, no smoke, no coal, and no fireman. Just a massive insulated tank filled with superheated water under pressure. These industrial workhorses were charged up at a central boiler station, then sent out to work for hours on stored steam alone. The concept dated back to the 1870s and found a perfect niche in places where open flames were suicidal. Ammunition factories, chemical plants, refineries, anywhere a single spark could level a city block. The charging process was spectacular. A massive hose would connect to the locomotive and pump in superheated water at up to 200 pounds per square inch until the tank was full. The crews called it feeding the beast. Once charged, the locomotive had enough steam for 8 to 12 hours of light work, but range decreased with every minute. Pull a heavy load, and you might only get 4 hours. The locomotives got progressively weaker as pressure dropped, eventually crawling along at walking speed before needing another charge. They were utterly reliable because there was nothing to break. No fire to tend, no complex valve gear, no boiler to explode. Industrial sites loved them, but for mainline work, they were hopeless. The Holman fireless proved that sometimes the simplest solution is also the weirdest. In 1935, the London Midland and Scottish Railway decided that locomotive pistons were yesterday's technology. The future belonged to turbines. They took a Princess Royal-class locomotive and replaced the entire drive system with a steam turbine that drove the wheels through reduction gears. The result looked almost normal from the outside, but was completely alien underneath. The turbine sat where cylinders normally lived, spinning at thousands of revolutions per minute, and connected to the wheels through a complex gear reduction system that would make a watchmaker nervous. The forward turbine was massive, designed for sustained high-speed running. The reverse turbine was tiny, just enough to back the locomotive into stations. This meant the turbomotive was brilliant going forward and pathetic in reverse. At speed, it was smooth and powerful. Starting from a standstill took forever because the turbine had to spool up. The maintenance was a nightmare. Turbine blades needed constant inspection for erosion. The reduction gears required precise adjustment. Any metal particles in the steam would sandblast the turbine internals. The locomotive ran from 1935 to 1949, spending about half that time being repaired. It proved turbines could work on rails, but at costs that made conventional locomotives look cheap. Only one was built. Number 4. The SNCF 232U1. French engineers in 1949 looked at conventional boiler design and decided it was too simple. They built a locomotive with a high-pressure water tube boiler operating at 1,450 pounds per square inch, nearly 4 times normal steam pressure. This was not just unusual, it was insane. The boiler looked like something from an industrial power plant, not a locomotive. Narrow tubes ran everywhere, creating a maze of pipework that defied understanding. The compound expansion system used steam 3 times before exhausting, squeezing every possible joule from the coal. But that pressure came at a cost. The boiler was temperamental, prone to scaling that would choke the narrow tubes. Water quality had to be perfect. Any contamination would cause deposits that could lead to tube failures. When tubes failed at 1,450 pounds per square inch, the results were catastrophic. Maintenance crews needed specialized training just to understand the system. Operating it required constant attention to water chemistry, pressure levels, and about 40 different gauges that all seemed to contradict each other. The 232U1 ran trials for several years, achieving impressive thermal efficiency. But diesels were simpler, cheaper, and did not require a doctorate to maintain. It remains proof that being the most efficient does not matter if you are too complex to run reliably. Number 3. The Soviet GT1, a turbine locomotive. In 1959, Soviet engineers decided that coal was for peasants. The future was gas turbines burning bunker oil. They built a locomotive that looked like a submarine mated with a fighter jet and sounded like the apocalypse. The GT1 had a massive aircraft-derived turbine sitting behind the cab, spinning at speeds that would make your teeth vibrate. It produced incredible power, rated at over 3,500 horsepower, making it one of the most powerful single-unit locomotives in the world. But that power came with problems that would make lesser engineers weep. The fuel consumption was biblical. At full throttle, it drank fuel faster than most locomotives used water. The exhaust was so hot it could melt rails if the locomotive sat idle too long. The noise was so intense that crews wore military-grade hearing protection and still went home deaf. The turbine needed constant speed to maintain efficiency. Throttling down meant burning fuel without producing useful power. Starting and stopping was a waste of expensive bunker oil. The Soviets built several units and tested them extensively. They worked, technically, but the fuel costs made them economical only on long, sustained, high-speed runs. When oil prices rose in the 1970s, the GT1 became a monument to impractical engineering. Number 2. The Chesapeake and Ohio M1 turbine electric. In 1947, Chesapeake and Ohio decided to build a coal-fired locomotive that used no coal directly in the cylinders. The M1 was a rolling power plant. A coal-fired boiler made steam. Steam spun turbines. Turbines drove generators. Generators powered electric traction motors. It was every type of locomotive technology crammed into one streamlined package, and the complexity was staggering. The coal handling system alone needed constant attention. The turbines were sensitive to steam quality and required sophisticated water treatment. The generators needed cooling, which added another layer of machinery. The traction motors were standard, but they had to handle power from an unstable source. Every link in the chain had to work perfectly, or the whole system failed. And fail it did, constantly. Coal ash infiltrated the turbines, eroding blades faster than anyone predicted. The boiler could not maintain consistent steam pressure under varying loads. The electrical systems overheated in the summer and froze in the winter. Maintenance crews quickly learned that fixing one problem often revealed 3 more. The M1 logged thousands of test miles, but it spent more time in the shop than on the rails. By 1950, Chesapeake and Ohio admitted defeat and retired it. The M1 proved that sometimes combining every good idea creates one magnificent failure. Number 1. the Norfolk and Western John Henry. This is it. The weirdest, most ambitious, most spectacularly complicated locomotive ever built. In 1954, Norfolk and Western gave steam one last chance against the diesel invasion. They built a coal-fired steam turbine electric locomotive that stretched 161 feet and weighed 800,000 pounds. Under that massive car body hid a coal-fired boiler feeding a direct drive turbine, which powered generators that fed traction motors on every axle. The boiler operated at 600 pounds per square inch. The turbine spun at 6,000 revolutions per minute. The electrical system generated enough power to light a small town. When it worked, it was magnificent, but it almost never worked properly. Coal dust infiltrated everything. The turbine blades eroded constantly, requiring frequent replacement. The generators ran so hot that cooling systems struggled to keep up. Every trip was an adventure in mechanical failure. Crews needed electrical engineers, turbine specialists, and traditional steam knowledge just to operate it. The control systems were more complex than contemporary aircraft, requiring specialists to maintain. In less than 3 years, Norfolk and Western gave up and retired John Henry. It was not scrapped, it was quietly hidden away. Too embarrassing to display, but too expensive to destroy. Steam's last gasp, a monument to over-engineering. And that's all, folks. These machines prove that the strangest ideas in engineering often push boundaries even when they fail spectacularly. If you enjoyed this, please subscribe for more locomotive history. Here is another video I have specially selected for you. See you next time.